Let's talk about function operations and composition. So we're almost done with this work. This whole discussion we've been having over the last 7 lectures was about functions. So we're going to wrap this idea of functions up now using operations and composition of functions. So let's define, first of all, function operation. We're talking about the kind of operation you do with numbers, real numbers, mainly addition, subtraction, multiplication, division. Remember, your numbers are a special case of functions, right? For example, just make up number 5. That is a function. Yeah, I can think of that as f of x equal 5. So number 5, I can think of it in terms of a function. So just as we can add, subtract, multiply, divide numbers, well, we can add, subtract, multiply, divide functions. So let's take a look at, for example, addition and subtraction of a function. So if I'm adding f plus minus g, that's addition and subtraction in one. This is how we write it. What does that mean? That means f of x individually plus or minus g of x. What does function multiplication look like? That's f times g of x. This time, that's when you multiply f of x times g of x. What does function quotient look like? That's f divided by g of x. That's when you do f of x quotient or divided by g of x. And anytime we divide by 0, of course, is undefined. So we make sure we recall or remember to say g of x can't be 0. Now when we say g of x not 0, for example, the denominator is x plus 5. We don't mean that this can't be, the function can't, the function itself isn't 0. We're talking about the values of x that makes that function 0. Okay? Now, what is the domain? Every function has a range and a domain, correct? So what is the domain of these functions? Well, for all of them, for all 4 operation, addition, subtraction, multiplication, division, we're going to say the domain is the intersection, correct? The intersection of individual domains. Individual domains of each of those functions. All right, so for example, I'm just going to make an example up here. Suppose I'm going to have a linear function and then I have a square root function here. Okay, and first I need to determine the domain of these because I'm going to need it in the end. So the domain of linear function, of course, all real numbers, negative infinity to infinity. The domain of g, the square root function, remember for all square roots the radicand must be at least 0, which means x has to be greater than or equal to 1/2, right? So this is going to be 1/2 to infinity. There. Now that we have the domains, let's do f plus minus g of x. And I'm doing both. Usually we have either addition or subtraction. I'm doing both. So that's going to be 8x minus 9, and then you either add or subtract depending on what we want to do, the square root of 2x minus 1. And of course you have a polynomial and you have a radical function. They're not like functions, so they do not combine. That's why I did it with a plus minus. Now, what is the domain of the addition or subtraction? It's going to be intersection of negative infinity to infinity. So I can actually do this. A graphical notation might help. This is the domain of f, right? Now, what is the domain of g? The domain of g, we said that that has to be greater than or equal to 1/2, right? So let's say here's 0. And this is 1/2. Greater than or equal to 1/2 would be everything above to the right of that. So the crosshatch is the intersection of domains. Therefore, the domain of f plus minus g is going to be from 1/2 to infinity. Again, the polynomial function has no issue with negative numbers. but the square root is going to run into issues, right? Even 0. The first function, when you put 0, you get -9. See, it can process it, no worries, no problem. You put 0 in for x, you get 2 times 0 is 0, minus 1 is -1. Square root of -1 is imaginary, right? Not real. So that's why it has to satisfy the domain values, must satisfy both functions. All right, let's take a look at, for example, the quotient function. F divided by g of x. See how that's going to work. So that means I have to do f of x divided by g of x, and f of x is 8x minus 9, g of x is the square root of 2x minus 1. Now, remember, we always safeguard against division by 0. We know that if division is 0, we have a situation where the fraction is undefined. So here, x cannot be 1/2. Remember, up here, it was okay to be a half because it was not in the denominator. So now, our domain, the domain of f divided by g is going to become, again, anything that's above 1/2, 1/2 to infinity. Look at this one and the one above it, bracket, parentheses. So one includes a half, the other one does not include. And again, because division by 1/2 gives you an undefined fraction. Okay. Now, having talked about some difference of functions, we're going to look at a very special ratio. This is commonly called difference quotient. Okay, so what is a difference quotient? Well, the word difference means you have subtraction of function. A quotient means ratio, right? So if I look at, to kind of give you a little bit of geometry for your eyes, so to kind of get a break from just pure algebra. Remember earlier we talked about secant lines, right? So let's say I have a secant line like that. And suppose that this point is x. This point is some h distance h later. So that's going to be x plus h, right? So delta x means changing x from this point P to point Q. The horizontal change is going to be h. And at the same time, this point is f at x, correct? And this point is going to be f at x plus h. All right, now I can look at the change in y, that's delta y. So if the ratio of delta y to delta x, remember that's going to be the slope of the secant line, right? So I can write that the slope of my secant line is therefore, as before, we've done this work before, is delta y over delta x. Now, delta y, change in y, is the higher point and the lower point here. So it's going to be f at x plus h minus f of x. So we have difference of two functions. So we're in the right section to talk about this. Divided by x plus h minus x. That would be simply the distance from here to the next point. All right. And of course, x plus h minus x, that's going to give you the h. Therefore, the difference quotient is formally defined as this quotient. Now, very simple. And I want to recall here, h is a constant here. It's not a variable. H is this distance here. So it's a constant number. And in our work, by the way, let me just mention h is extremely small. So what I've done is actually I've magnified h, this distance from P to Q in the horizontal direction. I've magnified that h, let's say 1,000,000 times. That's how tiny h is. But for us, this is the difference quotient. Now, this difference quotient, you will definitely work with this as you go to your calculus courses. This becomes interesting. This becomes the foundation of differential calculus. Amazing. Starts with this simple thing right there. and then we do go over in differential calculus through that. Okay, so let's take a look at the example. So what are we going to do with it? Because we're not in calculus, right? So what are you going to do with this in this course? Well, in this course, I'm just going to evaluate the difference quotient. Okay, now to do that, I need to find what f at x plus h is. Well, f at any point, you replace x with what's in parentheses. So I'm just going to put, instead of x, x plus h squared, and instead of x, x plus h. Right? Isn't that f at x plus h? And let's expand this and simplify and see what we're going to get here. Expand the binomial. Remember, when we expand the binomial, we end up with 3 terms. You square the first, twice first by second, plus second one squared. Distribute the 3. Negative 3 makes negative 3x minus 3h. Remove parentheses, distribute the 2. I get 2x squared plus 4xh plus 2h squared. Right? Oh, yeah, that's true. Negative 3x minus 3h. So you get expression like this. All right. Now let's do our difference quotient. Let's do f at x plus h minus f of x divided by h. So all of this is f at x plus h, correct? And I'm looking to see if there are any like terms. No. There are no like terms in that for f at x plus h. So I'm just going to have to copy it, the whole thing. 2x squared plus 4xh plus 2h squared, negative 3x, negative 3h. And then from that, remember, we're going to subtract. So I'm going to do minus, right? We're going to subtract the original function from it. This is the original function. I'm going to go 2x squared minus 3x. Correct? That's the original function. And then we're going to divide all of this by, let me see, let me draw a better line. There. All of that divided by h. Now we should be able to combine some like terms. The 2x squared, negative 2x squared are opposite, they add to 0. The double negative here makes positive 3x on the right side. So that positive 3x, negative 3x add to 0. Therefore, my difference quotient reduces to 4xh plus 2h squared negative 3h. Well, that's good. The 4 terms disappeared. Now, interestingly, you can see in the numerator, every term has h in common, right? So I can factor the h out, and that gives me 4x plus 2h minus 3 divided by h. And now I can divide the h's out. So all said and done. There you go. That would be the final answer. Okay. Now you may want to ask, well, so what, right? What does this tell me? What did I just do? Well, what did we just do is we just did this quotient. And yes, in this course, we know how to do the quotient. What does it mean at this point? It really doesn't mean much for us. But our objective is that, do I have the know-how? Can I do this at this level? Yes, we can. Now, as I mentioned again, when you go to calculus, they'll do something with this, and then the result will be something interesting. So let's try another one. What if I have f of x is equal to root x? Let's do f at x plus h. Remember, f at x plus h, you change your x in the original with x plus h. So that's just x plus h. And then our difference quotient is f at x plus h minus the original function over h. It's always this, the difference quotient. This time, I have f at x plus h is x plus h. And f of x is just root x divided by h. Now, see if we can simplify this one. So this is just a definition. Now let's see if I can simplify this. To simplify this, I'm going to multiply the top and the bottom by the conjugate of the numerator. Remember, conjugate of binomial, a plus b is a minus b, and vice versa. So I'm going to multiply. A is root x plus h, and b is root x. Conjugate means that has to be positive. And to be fair, I have to do everything to top and the bottom the same way. Good. Now, why did we do this for? Well, when I multiply two conjugates, let's do a plus b times a minus b. Remember, in our special factoring formulas in our review lectures, if you've forgotten, you can go back to review lectures in this for my college algebra. We get a squared minus b squared, the difference of two squares, right? So this is like a, and here is b. This is a, and here is b. All right, and the result's going to be, it's going to be a squared minus b squared, correct? So I'm just going to square x plus h minus square x squared. That's a squared minus b squared. And in the denominator, there's really nothing I can do. So I'm just going to carry all these factors, h root x times root x plus h. And in the numerator, we're going to have square root of x plus h squared is just x plus h. Square root of x squared is just x over the denominator. Again, everything intact. Can't do much there. Now look at the numerator. Isn't that something? I'm able to cancel the x's now. Right? So once we cancel the x, now the numerator is just h. Denominator is h root x times root x plus h. Think of h as h times 1. That's still h. Because I'm about to cancel, I need to have something. I can't leave a fraction blank. And that's 1 over root x times root x plus h. And don't worry about multiplying this. There you go. Check this out. Wasn't that cool? So we were able to, what seemingly was something we could not simplify, but with a little bit of clever insight, this was the clever insight, we were able to reduce it. So there we have that one. Let's take a look at another one. What if the function is 1 over x? Again, let me do f at x plus h. That's when you replace x with x plus h. So it's really that simple. And then we do our difference quotient. F at x plus h minus f at x divided by h. That's always going to be that. It's not going to change. All right. And f at x plus h is going to be a rational expression, 1 over x plus h. F of x is 1 over x. Oops. Minus divided by h. Now this is what we call a complex fraction, is where you have a fraction right over something that's possibly a fraction or not. H is not a fraction, but it's one of them is a fraction, and then you have fraction of the whole thing. Remember, this is called the primary fraction line, and these are the secondary fractions, right? All right. The easiest way, the fastest way to simplify this fraction is to multiply the top and the bottom by the LCD, which is x plus h. Right? The LCD of all denominators. And h, you can write it as h over 1. That's why the LCD of 1, x plus h. Those three is just, well, 1 you don't even consider. It's just x plus h. Now, if you do this correctly, by the way, this choice of LCD, next step, we have to have just an ordinary fraction, not a complex fraction. And let's see if that's going to happen. distribute the LCD to the first fraction. X plus h, x plus h. Those will cross out, right? So I'm just going to have x. Distribute LCD to the second fraction. This time, the x's cross out, so I have negative, parentheses x plus h, divided by. In the denominator, we have, again, everything. Nothing cancels or combines. And we don't want to distribute here, okay? Just keep it in factored form. Now, in the numerator, I can distribute the sign. I get negative x minus h divided by h x plus h. All right, and the x's cancel. And I can write negative h as negative h times 1 over h x plus h. The h's cross or cancel. And what am I going to have? I'm going to have negative 1 over x times x plus h. And there you go. If we do this correctly, again, we always end up with some in that step. That very last step, the h's cross out. Look what happened here. You see that? The very last step, h crossed out. Look at this one. So is this going to happen with every function? Yeah, it actually does. Okay. So there we have that one. Difference quotient. I think we've done a really good example of that one. Let's finish this work now with the last idea of this section is function composition. So we talked about, again, sum, difference, product, quotient. Let's look at function composition. Again, function compositions are very important in the higher math courses. So what do we mean by composition here? So just like I said, with functions, pretty much anything you do with numbers, you can do with functions. So with numbers, you can add, subtract, multiply, divide. So can you with functions. There's one additional operation you can do with functions, which we normally don't do with numbers, and that we can compose functions together. All right. So I'm going to use the function machine, the idea of a function machine here, to go through the next few examples to really clarify what's going on here. So here's a function, call it f. The machine has instructions to square its inputs. Okay, so that's the instruction to this machine. Let's say I'm going to put a 2. That's my input into the machine. A 2 goes in. What's going to come out? Well, 2 gets squared and the outcome is 4, right? And we say that's f at 2. The function evaluates 2 and the output is 4. So f at 2 is 4. And that's no surprise. We've seen that before. We saw that in, like, I think it was lectured in section 2.3 that we introduced the functions then. Let's do another one. Okay, so for instance, let's say I put a 10 in this time. Input 10. When 10 goes in, what comes out? Well, the machine does what it's supposed to. It will square it. It says, okay, there is 100. So corresponding to a 10 is that number, 100. The output. Now, we can create a chain of functions. We can compose these functions in a way that the outputs from the first function is then input into another function. Okay, so this time I'm going to use, let's say, here's my other function. Function g, I'll make it easy, x plus 5. So what is this function going to do? Well, the task of this function is to add 5 to whatever that goes in. Okay, so let's take a look at the input 2. Remember, the output from f was 4, so 4 is going to go in here. And of course, this function has to have an output, so we're going to put an outlet there. So what's going to come out? When 4 goes in, well, G does what it's supposed to. It adds 5 to it, and there we have 9. So that's the idea of composition. You just link, you chain these functions together. Input into first produces an output. The output is in turn becomes an input into another function, and then it produces an output. So we can link as many of these as we want. Okay, there is no really restriction as long as it's a finite number of chain we can form or linkages. Usually in this course we look at composition of two functions f and g. And there you have it. Now let's track our 100. Let's see what happens. 100 goes in, G will process it, right? G will process, so that 100 plus 5 becomes 105 now. You see how that works? It's really that simple, the idea of function composition. So how can we write what just happened here? The fact that the first machine, f, processed x squared, so I'm just going to put f of x, that's the process through the first machine. And then remember, we output this as an input into G. So there I have G of f of x, and in fact G of f of x. That's how we read this. Okay. Keep in mind again, the inside function was executed first through the first machine, and the outside function was the second one due to the second machine. Now, this composition, we can actually use composition notation, and we're going to write it like this. We're going to put G circle f close paren of x. And be careful, we're doing G open circle f. If you put a dot, that's the product function, right? This is the product function. Be careful. We're not doing that. We're doing the circle notation, right? That's the circle notation. And we read it exactly as I read it here, and I wrote it. G of f of x. Now, if you change the order of the machines, by the way, you don't expect to get the same output. The order of composition, I should say. Okay, so I can write down then what happened. The one that we are looking at up here, we did G of f of 2, and the final output was a 9. When we did 10, we did G of f of 10. Remember, 10 got processed, gave me 100, and G added 5 to it. The final output is 105. Okay, now we could have done this, and this is how we want to do it. Let's keep x now general instead of 2, 10, 5, 0, negative 1/2, and so on. Let's see for a general x, what is the final output going to be? Remember, these are the final output once it goes through the composition. So G of f of x, that means the inside function is processed first. The inside is x squared. And then it's passed on to G, right? The output of x squared is passed on to G. What will G do to it? It will square it, add 5 to it. So there you have it. This is the result of the composition. Now, let's see how we're going to use this. Rather than doing the function machine and processing 2 and tracking it at every point, I'm going to go G of f of 2. We already know the answer, right? The answer is 9. That's going to be G of f of 2. Again, you change x with a 2, you square it. That becomes G of 4. And G of 4, you plug in 4 into G, and remember G was x plus 5. That one. So I'm going to actually do 4 plus 5. The answer is 9. You see, we get the exact same output. Let's do G of f of 10. So G of f of 10, well, f, the function f will square the input. The output of that is 100, and G processes 100 by adding 5 to it. You get 105. This is again without going through this whole function machine notation. But it's really a good way to illustrate and show how this composition takes shape. I mentioned if I change the order of composition, typically we don't get the same answer, so let's do that. Instead of G of f of 2, let's do f of G of 2 now. Remember, let me just for reference write down our G of x was x plus 5, and our f of x was x squared. Okay, so what does G of f of 2 looks like? Or I'm sorry, f of G of 2 looks like. Well, we worked the inside function first. With compositions, you work these from inside out. Inside, outside. Okay, so that means I need to do G at 2. Well, G at 2, remember, you change x with 2 here and here. So that's going to be 2 plus 5. So G at 2 is 7, isn't it? That's what G is going to output. And then we're going to feed the 7 into f. What will f do to its inputs? Its task is to square them. It will square it, and the output is 49. We see the numbers are different, right? F of G of 2 in my example does not equal to G of f of 2. Again, this is a lot of times this is the result. Will there ever be a case where the two are equal? Yes, they will be. Only for a select group of or category of class of functions, namely the inverse functions. If two functions are inverses of each other, then the order of composition doesn't matter. But for the work we do, we haven't even talked about what inverse functions are. So yeah, in general, that is not the case. So I'm just going to put note. In general, that means typically, okay, f of G of x does not equal to G of f of x. But then there are instances that they will work, but in general, they're not going to work. The order of composition matters. It's better safe to say they don't work, so we don't just assume that it works. And then for the ones that it work, you say, wow, check it out, it worked. Now, let's do the general now. We just did f of G of 2 and we got 49. Let's see for the general input x, what will the final output be? Working from inside out. Remember G of x was x plus 5, correct? So I'm just going to write x plus 5. Now what is f going to do to x plus 5? It will square it, doesn't it? So it will take the input x plus 5, and of course, indeed, it will square it. And if you square the binomial, you get x squared plus 10x plus 25, if you want to. Now, we just did f of G of 2, we got 49 up here, right? Let's check it out and see what we get now. So I want to do f of G of 2. We go right to the end. There you go. That's the final output. Which is really, it was this one, right? So it's going to be 2 plus 5 squared or 49. There, you get the exact same results. This is how we want to handle these compositions, by the way. Okay. Now, how do we determine, because function composition of function gives you a function. So how are we going to work these compositions as far as the domain goes? What is the domain of the composition function? So let's say the domain of f of G of x or G of f of x, whichever we are working with. We usually work with one or the other, not both at the same time, one or the other. So the domain of this is going to be all numbers x in the inside function, right? Remember f of g of x. Let's say I'm doing this one. For f of g of x, it's going to be all numbers in x, which is are all numbers x in function g, such that g of x is in the domain of f. Domain of f. Now, to keep this simple, let me do that. Forget this or. We're looking at the domain of f of g of x. Again, so it's going to be, again, all numbers x. Okay. In g, on the inside function, so that the output g of x is in the domain of f. So we got to really keep track of two domains. Okay. In terms of our machine, this is what our machine looks like. So here we have g. So we got to be in the domain of the first machine, x, because g has to be able to produce an output, right? If g cannot produce an output, then f will never actually kick in. It will never work, right? Then g is fed into f. So what goes in f? Now f should be capable of producing these numbers. So we look at the domain here. And then the output is going to be f of what g has passed on to it. F of g of x. All right. Now let's take a look at an example here, just to clarify what we've done. Suppose my f of x here is going to be 6 over x minus 3, and I'm going to make g of x also a fraction, 1 over x. So first, what is the domain of the function? Because it's a rational function. Domain is all real numbers, except what makes the bottom 0. So x cannot be 3, because if it is, we get 6 over 0, which is undefined. Domain of g will be all real numbers except what makes the denominator 0. So for this one, x cannot be 0. Therefore, keep in mind, in our toolbox of numbers, we are not given 0 or 3. Now, let's do the composition of f of g of x. The outside function is f, the inside function is g of x. So I'm just going to put 1 over x, right? That's my g of x. What is f going to do with this input? Well, f is going to do 6 divided by whatever input is, which happens to be 1 over x. And then it will subtract 3 from it in the denominator, right? That's what f does. This is again a complex fraction. We can simplify this complex fraction by multiplying the top and the bottom by LCD, just x. And when we multiply top bottom by LCD, what are we going to get? We're going to get 6x on top, and in the bottom, x times its reciprocal is 1 minus 3x. And there we have a rational function. So this is our composition. See how simple that was? Now, what is its domain? Well, the domain of this one, if I go back to my function machine, remember, we started with g. G was 1 over x, right? So the output from this is going to be g of x, 1 over x. And this is going to be going inside function f. And what will f do to this one? F will, to its inputs, it will do 6 over x minus 3, right? So what goes in here? Again, remember, x cannot process f. F cannot process a 3. So any fraction in g that feeds a 3 into function f will cause this machine cease to work. Therefore, the inputs into f cannot be 3. These are the inputs out of g. They cannot be 3. So if I cross multiply and divide by here, divide both sides by 3. So x cannot be 1/3, correct? And you can and you can try it. Let's do that. Let's actually put in a 1/3. Let's violate and see what happens. In this machine, input is 1/3. The thing we are not supposed to have. I'm going to put 1/3, see what happens. So g at 1/3. See, g has no problem. It says, okay, I'm going to do 1/1/3. I'm going to pass on a 3 to f. Right? This is going to be passed to f. Now, f is going to do at 3. F is going to try to evaluate it, right? Aha, there you go. You see that? F comes to a halt. So I cannot do division by 0, undefined. There will be no output. That's why we exclude 1/3. Okay. Now, here's something that's interesting. To begin with now, remember for this composition, to begin with, what if I put in a 0? Well, 1/0 is undefined. There will never ever be an output from G for F to process. Although F is perfectly capable of processing zeros, right? Look at F. The function is here, right? Can it process a 0? Of course. Put 0 here. 6 divided by 0 minus 3 is -3. 6 divided by -3 is -2. So F has no problem, no issues with 0. It's just to begin with, X cannot handle it. Even in here, see, 0 divided by 1 minus 0 is 0 by 1, which is 0. So what's the problem then? Well, the problem is, remember, I said to begin with in our toolbox, we are not given 0, we are not given 3, right? Right, for these. So we're looking at now for the composition of f of g of x, we're looking at exactly this configuration. So all said and done, the domain of f is going to be the numbers that g cannot process. X cannot be 0, and the outputs that are passed on to f that f may not be able to process. And that one we just showed was 1/3. So our domain is therefore, there you go, everything but that. Notice, by the way, we said f cannot process a 3, right? So the only time a 3 will enter this machine is when x is 1/3, right? So if I put 3 in the beginning, that's fine. 1/3 comes out. See, when you put 3 in here, a 1/3 comes out, not a 3, and a 1/3 goes into f. F is okay handling 1/3, right? 1/3 minus 3 in the denominator, and it'll be able to handle it. Now we can write the interval notation for this one. If I look at the number line, -infinity, let's say here is 0 and here is 1/3 are exclusions. Everything else is fine. So the interval notation for each segment will be -infinity to 0, union, 0 to 1/3, union, 1/3 to infinity. And that will be the interval notation for this one. The domain of composition is not trivial. True, it's not. It's like, oh my gosh, that's a lot of work just to get the domain out of this. The composition itself is easy to do. The domain takes a little bit of work. So let's do g of f of x now. Well, g of f of x is going to be g of 6 over x minus 3. That's what f of x is. And what will g do to its input? Remember, it does 1 over x, so it's going to do 1 over 6 divided by x minus 3. Invert and multiply, we get x minus 3 over 6. Let me write this in the form of 1 6x negative 1 half, right? X by 6 and 3 by 6. Because the reason I want you to see this as mx plus b, this is a linear function, isn't it? Remember, we said the domain of linear function is going to be all real numbers, right? Except vertical lines. So, but let's see if it actually is capable of handling everything. So our composition is g of f of x. So f has to be able to process its inputs first. Remember, this is machine f. What does f do? F instruction to f is to do 6 over x minus 3. The input, output, f of x. So I cannot put in a 3 here, right? I get division by 0. So x cannot be 3. To begin with, I cannot pass on 3 to f and then say give that to g. There will never be an output. Nothing comes out of that machine. So here's our exclusion now. This is where we need it. And then we're going to feed this into g, right? Remember what g was doing? G does take the reciprocal. That's all g does. And then it will output its results. So when will g, just isolate this machine, when will g not be able to have an output? Is when you divide by 0. That's when a 0 goes in, right? So if I pass on a 0 somehow, a 0 output from f of x, then g will not be able to process it. So the question is, can f of x be 0? If it is, for what value of x? So that we need to exclude that. So far we have one exclusion. We know it cannot be this because f cannot process it to start with. Now let's look at our function f of x. F of x is 6 over x minus 3. Set it equal to 0 and see what makes that 0. Well, this is a fraction. In a fraction, the only way a fraction is 0 is if the numerator equal to 0. True? So you have 0 over non-zero and 0. That's what we're saying. Now in this case, look at the numerator is 6. 6 is never equal to 0. So nothing makes this fraction 0. True? Because the numerator is always 6. Therefore, there will never be an output of 0 from this composition, right? There will never be an output of 0, not from composition, sorry, but from f, from function f. So g is going to be okay. It will never be passed on as 0. See that? It will never be passed on as 0. So g is going to work just fine. The composition is this, and the domain of g of f, therefore, is going to be all real numbers except 3. The very first thing f cannot process. In interval notation, that's everything on the number line up to 3, to the left of 3, and just to the right of 3 to infinity. And there we have this domain. All right. So we talked a lot about, again, function operations. And we talked about function composition was the biggie here. Now let's take a look at some exercises here, and that will be it for our work. Okay. Now in our exercises, first we're going to look at the basic addition, subtraction, multiplication, and division. All right, let's take a look at those. In our examples, let's take a look at, for instance, let's say these will go fairly quickly. 3x plus 4 and g of x. That's going to be 2x minus 5. Okay, well, let's do all the operations. Let's do f plus g of x. Okay, f plus g of x, that means you do f plus g. 3 and 2 makes 5x minus 1. Domain of f, all real numbers, is linear. Oops. All real numbers. Domain of g, also all real numbers. So that's good. You're given all real numbers in both functions. They're cool with it. The final function is a linear function, so its domain is all real numbers also. That's for f plus g. F minus g of x. So we do 3x plus 4 minus 2x minus 5. That's going to be 3x plus 4 minus 2x plus 5. Combine like terms. 3 minus 2 is 1x. 4 and 5 makes 9. There's my linear function again, capable of handling anything, and everything is given, passed on to both functions. Cool. Let's do the product function, f times g of x. F times g of x, we multiply f of x and g of x. So we're going to do 3x plus 4 times the binomial 2x minus 5. Do FOIL, we get 6x squared negative 15x plus 8x minus 20. And this will give me 6x squared negative 7x minus 20. A polynomial function capable of handling everything, negative infinity to infinity. Notice, by the way, we didn't talk about the range, so our concern is really with domain rather than range here. Okay, let's do the quotient function. The quotient function is going to be f divided by g, right? 2x minus 5, sorry. There. And we can't divide, right? We cannot divide individually, so that's it. Now this fraction can handle anything except the values of, remember, this is f of x over g of x. And we said g of x cannot be 0 when we did this work. So what makes the denominator 0? Let's find out. Looks like 5/2. We're going to exclude it. So domain is all real numbers, negative infinity up to 5/2, just to the right of 5/2 to infinity. All right, and that's the domain of this one. So these are pretty, again, straightforward if they're a polynomial function. Let me make an example. What if I don't have a polynomial function, something like 4x minus 1. I will make this one a fractional function, right? A quotient, a rational function. Some differences. Oh, the domain, sorry, the most important part. Domain of this one, for square roots, the radicand must be positive. 0 is the minimum it can be. Therefore, domain of f is going to be 1/4 greater than equal to 1/4. Domain of g, well, g can be anything except division by 0, so x cannot be 0. So keep in mind, can't be 0, g cannot handle 0, f cannot handle anything below 1/4. Now let's do the sum difference. I'm going to go sum difference here because, again, these functions will not combine. So the sum function would be plus, the difference would be minus 1 over x. These are two different functions. I'm just combining them as two operations into one. And what is the domain of this one? Right? The domain of this one is going to be x has to be greater than or equal to 1/4, right? And that's going to be from 1/4 to infinity. Now, remember, and the reason I didn't put the 0 is because if you look at the interval from 1/4 to infinity, you're already excluding 0, aren't you? See, 0 is outside that interval, so I don't need to say x cannot be 0. The intersection, remember we're talking about the intersection of domains. The intersection of two would be that. So the 1/4 to infinity handles the fact that x cannot be 0. Let's look at the product formula, f times g of x. Again, f is the square root of 4x minus 1 times g is 1 over x. If you want, you can write it as root 4x minus 1 over x. All right, again for this one, because in the numerator it has to be 1/4 to infinity. We know here x cannot be 0, but this interval doesn't include 0 anyway, you see up here? So we acknowledge it, but there's no reason to account for it here, because 1/4 to infinity already excludes 0, right? It's not in that interval. 0 is not. Let's look at f divided by g of x. And by the way, we're doing f divided by g. If you do g divided by f, we'll do that one. You get a different composition. I'm sorry, it's a different, not composition. These are fractions. This is a different quotient. With f, because remember, division is not commutative, so it makes a difference what goes on top, what function on the bottom. And this is the function on top. The function on the bottom would be 1 over x, which you invert and multiply, we get x times 4x minus 1. And in this one again, 1/4 to infinity. And note, by the way, for this one, 0 is okay. It can handle 0, but intersection of domains. This cannot handle a 0. See, you get 0 minus 1, square root of negative 1, imaginary. So for that reason, we don't include 0. All right, now let me show you just g over f. This is what I was saying. To do g over f, you do 1 over x divided by square root of 4x minus 1. And this time you get 1 over, multiply top bottom by x. I get 4x minus 1. Look at this one. Again, the denominator has to be 1/4 to infinity. We know x cannot be 0, but see, 0 is already not in that interval. We don't need to account for it separately. Right? And there we have it. And let's take a look at now. We did enough difference quotient, I think. We're good on that one. Let's do a composition. Okay. So for our composition now, suppose, let's say my f of x is 2x minus 3 and g of x is negative x plus 3. And suppose I want to do f of g of 4. So f of g of 4, first I'm going to write it in the form that I understand it, in this form, rather than the circle, the fog notation, fog, f circle g is the fog notation. So g of 4, remember, we plug in a 4 for x in g. So we're going to get f at negative 1, and then we're going to pass this on to the function f. F we do 2 times the input minus 3. The final answer is negative 5. Okay. What if I want to do g of f evaluated? Let's go easy on ourselves, 0. Well, this time the outside is g, the inside is f. It really helps us, by the way, to think of these as truly what they are. G is called the outside function. F is called the inside function. If you try to remember this in your higher math, this is really going to help you a lot. All right. So remember what f does. F is square root of 4x minus 1. So f at 0 will make this 4 times 0 minus 1. True? 4 times 0 minus 1. 4 times 0 is 0, and 0 minus 1, aha. Let's see, the function f, oh, I'm sorry. The function f was actually not the square root. This was f of x, 2x minus 3. So f at 0 would be 2 times 0 minus 3. and that's g at -3, and g is, I'm still back into the previous one, square root 1. And g at -3, you pass -3 to g. G will do what it's supposed to, right? G will do this. It will take negative of the input, adds 3 to it. So that's going to come out as a 6. All right. And I know we are about an hour. Let me do just a few more, because this section really does require we do more examples. The composition part does. So let's say for this one now, f of x is root x and g of x is x plus 3. Okay, and for this one, we want to do f of g of x and g of f of x along with their domain, okay? We want the general form now. So f circle g of x, outside function f, inside function g. So that's going to be f of x plus 3. The way f handles the input, it takes the square root of its input, and there we go. That's what that one is. What's the domain of the radical? It's going to be -3 to infinity. Oh, I forgot to write that. The domain of f, what f can process, x greater than or equals 0. What's the domain of g? G is a linear function. G says, I'm cool. I can handle any input. All right. Now, once we get the composition, notice to handle this composition can only handle when the radicand is going to be -3 or higher. So the radicand is always positive, right? That's the only time this works. -3 to infinity. So the fact that f says I can only handle positive numbers, that's fine, because we want, let's see in here, the intersection of domain. Remember, g is processing first. That's x plus 3. So output from this could be all real numbers, right? Output from this is going to be x plus 3. And that will go into the machine here. If x, and what does f do? F takes the square root of it. So as long as this is positive, greater than or equals 0, then the f machine is happy. G's got no problem handling any input. So our domain is going to be -3 to infinity for this one, for f of g of x. Let's do g of f of x. G of f of x is going to be g of square root of x. So remember, this time now, we're working with the square root first. X has to be greater than or equals 0 here. So we know that. Otherwise, there will be never an input into g. But once a valid input goes into g, g will add 3 to its inputs. Okay, so what is going to be the domain of this one? X greater than or equals 0, which means bracket 0 parentheses infinity, right? 0 to infinity. That's that one. And there we have the composition. Let's do one last composition here. Suppose I have f of x is 1 over x minus 2 and g of x is 1 over x. And let's say we want to do f of g of x. Okay, the domains. Domain of f. F says, don't give me 2. I cannot handle 2. Domain of g. G says, do not give me 0. I cannot handle 0. Okay, so f of g of x is going to be f of 1 over x. This will be passed on to f. F would do 1 over the input minus 2. Multiply top and bottom by, let's multiply by x to get rid of complex fractions. So what will this become? The top's going to be just x, right? X times 1 is that. Bottom, you distribute, you get 1 minus 2x. So there is the composition. Now remember, we have f of g of x. So we're going to look at, again, what's going to be passed on to f right in here. X cannot be 0. We know that. Because then there will never be an output from g. And what about f? F, remember, again, the machine really, I'm hoping the machine really helps you visualize how this composition works. For domain, it's a pain in the neck, folks. That's why I want to make sure you get this right. So we're doing first inside function. There you go, 1 over x. Out comes 1 over x. This goes into g, right? I'm sorry, this is g, right? This goes into function f now. F does 1 over x minus 2. So the only thing that will block, if you will, that will jam this machine is if x is 2. Agreed? If x goes in a 2, as a result of 1 over x, there comes a 2. 1 over 0 undefined. So we need to know when 1 over x can be 2. Multiply both sides by x, divide by 2. So if you put in a half in here, out comes a 2, and that will jam the second machine. So we cannot have 1/2. X cannot be 1/2. Okay, therefore for this one, the composition, x cannot be 1/2. And remember, a 0 to begin with will jam the first machine. So x cannot be 0 either. We already mentioned that up here. So all in all, x cannot be 0 or 1/2. In interval notation, we want to exclude a 0 first, right? So that's going to be negative infinity to 0. And then it goes clear up to a half, stops at a half, then it goes from half to infinity. That's how we exclude 0 and 2. Now, depending on what the book or examples in the books ask you, some are happy with just x cannot be 0 or 1/2. But the others will actually want the interval notation, which I have down here. Okay, and there you have it. This is f of g of x. Okay, now your g of f of x will be different. See if you can try the g of f of x. And now, one last idea, and I'm just going to finish this lecture. Let's say in this example, we talked about composition. So suppose my composition, I have a function h of x, and I'm going to write it as 6x minus 2 squared. Okay. Now I want to see if I can write this h of x as some f of g of x. Okay. In other words, I want to write it as a composition of two different functions. Okay. So how are we going to do this one? Okay, and there's more than one way to do this, by the way. So for instance, again, h of x, I want it to be f of g of x. If I think in terms of the outside function, so the outside function is some kind of a square, isn't it? Because I see the 2 on the outside, superscript and parentheses. So this is the outside function. And what will the inside function be? Well, inside is clearly like 6x minus 2, right? So whatever that is, 6x minus 2. So my outside function, therefore, I'm going to go f of x squared. You see that? The basic function, regardless of what's inside. And I'm going to let my inside function be g of x, what you're seeing, 6x minus 2. Now let's do that composition of f of g of x. For instance, if I do that, that's f of inside I said my inside function is 6x minus 2. So how will f process this? This is my f. F will square its inputs, right? There you go. See how that worked? So this would be a way to visualize function compositions. Some functions could be visualized as composition of two or more functions or on their own merits. Okay, so that's what that is. Let me do another one. Let's say I want to do a square root 1. That's the root of x squared minus 1. Okay, so for this one, what are we going to do? Again, the outside function, the prevailing function, is the square root function, right? This is outside. The inside function is what's under the radical sign, x squared minus 1. So we're going to go outside f of x is the square root of x. The inside function would be g of x, and that's x squared minus 1. And what are we going to write here? We're going to go f of g of, let me go a little bit lower here. So f of g of x, that composition is going to be f parentheses the outside, the inside, and the inside is x squared minus 1. This will be passed on to g. What is g going to? Yeah, that was g actually. The inside is g of x. The outside is f of x. And inside is going to pass it on to the outside. Outside is the radical. Anything you give it, square root of x. It will just put a radical over it. What's being passed on to it is x squared minus 1, and there we have that one. So we're done. Again, sorry the lecture took a little longer, but again, there was a lot of good stuff in this section we had to cover. So hopefully you're good. We talked about function operations, and function composition was the key concept here. Thank you for watching, and hope you followed everything we did in this video.